surround the atom, uh, and with the idea of following obey the octet rule, because we mainly discussed on the atom, on the element S and B. That means the element in the first and second rows. Of course, we know some exception, as
Mặc áo
the
vào
octet
ấm
rule
nào.
can
Mặc
be.
áo vào.
Em khoác cái áo ấm nào. Áo bảo là công nghệ gửi đấy nhá.
Không gửi,
Không có điểm đâu nhá.
không cần điểm.
Điểm đây.
When's our mic? Turn off your mic, please.
Đây
Thank you. Okay. So now you know very well that in one thing you should remember, chemistry is experimentation, it's experimental science, not theoretical science, not imagination of human being, but we use imagination of human being to explain what we see, what we observe in the nature. And in the nature, you understand that the molecule are not having just 2D dimension, but they have a 3 dimension. That means they have a 3D structure. So how can we now convert from 2D structure on the paper by language structure to the 3D structure to approach the reality in the nature? Then when we have this geometry, we will discuss back the question of the polarity, because the polarity of one compound decides the reactivity, stability, but at least one physical property important, which is solubility. We know that like dissolve in like. That means one polar compound will dissolve in polar solvent, one non-polar compound will dissolve in non-polar solvent. So how we can form the polarity of one chemical bond can convert to the polarity of one whole compound when we know the 3D structure of this compound. And also this lecture we will discuss about the theory to describe the chemical bond, not by only sharing the electron, because we understand from the last lecture that you have a difference kind of chemical bond from the metallic bond to the ionic bond and covalent bond. So this lecture we will mainly discuss on the covalent bond, saying that we will discuss different theory that can be used to explain the covalent bond in a chemical compound, and we will emphasize its limitation of one theory when we discuss the bonding. Okay, so we look at the content, of the heavy content of this lecture. First, we will discuss about the molecular shape, so the geometry of molecule. We then move on the VSEPR model. That means representing for the valence shell electron pair repulsion model. V representing for the valence, S for cell, E for electron, P for pair, and R repulsion. So you have a valence shell electron pair repulsion model. Then we will discuss on the molecular polarity. In the fourth content, we discussed on the covalent bonding and the overlap of orbital, how we look at the orbital and how the orbital overlap can generate the covalent bond. We will discuss on the concept of hybrid orbital. In the previous lecture, you learned about the orbital S, P, and D. Now we will discuss on how the orbital will be mixed. We combine the orbital S and P to make the orbital SP hybrid orbital. You mix orbital SDD to combine to have orbital hybrid orbital SDD. So when you have a hybrid orbital, that means you have an orbital which have a both character of orbital S and character of orbital B. So we call the hybrid orbital. We discussed on the multiple bond, not a single bond, but the double bond, triple bond, and so on. In the previous lecture, before discussing about the nature of the bonding, we understand that the single bond is longer than the double bond and longer than the triple bond. And also we know that the single bond is weaker than the double bond and weaker than the triple bond. All of the tendency we know already, but now we will look at the bonding, how the single bond and double bond and triple bond will be created. And also one thing we will discuss at an exam, how the bonding difference will decide several important physical property of chemical compound. For example, the conductivity, electrical conductivity. Why one compound like old sigma bond, like diamond, is non-conducting, but when you have a double bond like graphite, polymorph, the carbon, the same carbon like carbon, same carbon like diamond, but the graphite is highly conducting, one of the best conductor we know today. And then the last section, the last part of this lecture, we'll talk about the molecular orbital. That means now we will not only consider about the atomic orbital, that means orbital of one atom, but we consider the whole molecule like one. Not one molecule consists of several isolated atoms, and we talk about the orbital of different atoms. Now we mix all together, we consider one molecule like one object unique, and we discuss about the molecule of the orbital of this molecule, not the orbital of individual atom in this molecule. So we have concept of molecular orbital, and when we move to the concept of molecular orbital, one of the most advanced theory in the chemical bonding, we can describe, we can explain several important chemical reaction, several important physical property, especially when we talk about the excitation state. Okay, so let's we go first on the geometry. So here you have the language structure of the molecule CCl4. When you draw this structure on the paper, okay, you can imagine that you have four bonding exactly identical, and you can imagine that the angle CL will be 90 degrees. Okay, will be strong. But as we imagine from the language structure on 2D on the paper, in reality, when we take this compound and we get the real structure by diffraction, we have the molecule in the 3 dimension like this one. And when you link the 4 chlorides, you will have this tetrahedron. You have a tetrahedral structure. And the angle between chlorides, carbon and chlorides is not 90 degrees, but 109.5 degrees. It's much higher than 90 degrees. That means the distance between the chloride and chlorides, in this case, the Cl will higher than the Cl in the case of language structure. And you understand that the chlorides here have 6 non-bonding electrons surround. So that means the electron density surround on this atom is very high. So, and the electrons have negative charge. So longer the distance between the 2 chlorides make the molecule more stable, because the interaction between the 2 negative charge population will be reduced. So you can imagine that if you put a language structure 2D like this one on the paper, it looks beautiful, symmetric, but it's not stable. It's less stable than when you arrange the chlorides in a 3D structure and 3D dimension. In 3 dimensions, so the interaction between the chlorides will be optimum. So you see the motivation why you need to move from a 2D, that means 2 dimension, to 3D, 3-dimension structure, because it reflects the reality, the nature, and also when the atom arranged in 3D, it makes the molecule more stable. And in the nature, the the atom will arrange in the fashion that make the molecule much more stable. That means at the lowest potential energy. So that's for the exam. So let's we look at different simple molecule. When you have a molecule of 3 atoms, AB2, then you can have linear structure. You can have also band structure. It means the 2 atoms this bonding angle is smaller than 180 degrees. For the case of AB3, you can have the arrangement perfect trigonal planar. That means the angle between oxygen, sulfur, and oxygen exactly equal to 120 degrees. You will have another arrangement. You can imagine that here, the 3 atom fluorides on the same plane, but the nitrogen is above of this plane. Okay, so you have trigonal pyramidal. That means it's make a kind of pyramid. And you have you can have also T shape. Very easy to imagine here. So here you have a other geometry, like you have theta hero, like for the KFC CL4, you can have 5 atoms like this one. You have a trigonal pyramid. I mean, x half of this one is one pyramid, So you have 2 half of pyramids put together, share the same plan. So you have a trigonal pyramid B pyramid. You can have also octahedral for one molecule with 6 atoms. So all of the angle will be 90 degrees, and the bonding will be exactly identical. So we have a very perfect symmetric octahedral. So in the case of complex, for example, if you put the cobalt in the water, you have a cobalt surrounded by 6 molecules of water. So you imagine the exam we want to talk about the splitting of the d orbital previously. The 5d orbital, you remember that's of the cobalt, you have 5d orbital. And before putting in the water, the 5d orbital will be exactly similar. But when you put surround by the cobalt in the center by 6 molecule water, the 5 orbital d will split in two groups. One group of 2 orbitals much higher because it's aligned on the z and x, y, x, and the 3 other d orbital at the lower energy. So we discussed on that. That makes the dry cobalt have no color, but when you put the cobalt in the water, it becomes color. You can observe the color. Okay. That's also one motivation we need to learn about the geometry of molecule, because it can explain the physical chemical property that means the absorption of the camber. Okay, now we move to the second concept. We call the valence cell electron pair repulsion model, VSEPR. So we talk about the electron domain. Well, when you have a one atom, you have different number of valence electron, and you use the valence electron to make the covalent bond. Okay, so you can imagine that you have 4 electrons in the valence cell. That means you can have maximum 4 single atomic orbital with x orbital have 1 single electron. That also means this electron, this atom, sorry, can have maximum 4 electron domain. Okay, electron domain, that means a space in the electron domain is a volume of space where you can find electron. It's quite similar to the concept of orbital. So you know that one place the electron can be localized there, then it means you can have a chance to have a negative charge in this position. So in the space, if you have a 2 place where you can find electron So you can have a two population of negative charge. So the two population can have repulsion interaction because they have the same negative charge. So they will try to expand the two domain maximum get farther possible to make the system more stable. So let's say with this idea, in this case, for example, you have one domain with electron here, negative here, and another electron domain here. So basically, it will have the interaction to make the two domain as far as possible to minimize the interaction. So in the case of two electron domain, so the best arrangement will be a linear arrangement with the distance, with the angle between the two, between the 3 points, become 180 degrees. So in this case, it becomes optimal in terms of interaction. If you have three domains like this one, so the three domains will try to experience each other as far as possible on the same plane. So the optimal arrangement will be the trigonal planar, where the angle will be 120 degrees. In the case you have 4 electron domain, then the arrangement now will be theta hero, where the angle of the two domains with the center will be 109.5 degrees. This arrangement will give the optimal interaction of this negative charge. Optimal interaction, that means the system will have lowest potential. So the take-home message is the best arrangement of a given number of electron domain is the one that minimizes the repulsion among the repulsion because they have the same negative charge. So we will see that the arrangement, in other words, the geometry of molecule depend on the number of electron domain. If you have a 2 electron domain, it's very likely that it will have a linear structure. If you have a 3 electron domain, the best arrangement will be trigonal planar. If you have 4, it will become theta hero. If you have 5, it becomes p pyramidal. If you have a 6 domain, so the best arrangement will be octahedral. Okay. So now, if you use this valence shell electron pair repulsion model, how can we predict the shape of one molecule? So the geometry of one molecule or an ion. Let's take the case by standards of Na3. First, you know how to draw the Lewis structure. So you have this Lewis structure. In this Lewis structure, you know that you have one pair of non-bonding electrons. That make Na3 become a Lewis base. Now, after drawing the Lewis structure, we will see the number of electron domain. So you will have one pair of non-bonding electron. You have 3 sigma bonds. So in total, you have 4 electron domain. Okay. So when you have 4 electron domain, the best arrangement will be theta-hedral, as in previous slide we know. So in this one. So in reality, the non-pair electron is something you can imagine, but experimentally you cannot observe. So that means when we consider about the number of electron domain, we should consider about non-bonding electron. But when we look at the real geometry of molecule, we should exclude the non-bonding electron because experimentally we can observe only the bonding. We cannot observe the non-bonding electron. So to exclude when you exclude this one, you will have a final structure, because here you have a non-bonding, and you exclude, you have the structure final, where here you have a nitrogen in the center with the 3 hydrogen around. So you will have trigonal pyramidal geometry. So this will be the final geometry of the molecule Na3. Okay. So by learning this exam, you can see few steps when you want to predict the geometry of one molecule. First, you need to draw the Lewis structure and pay attention on the bonding electron, on the non-bonding electron. And then you do the calculation for having the total electron domain of the central atom. Here is nitrogen. And you need to calculate both non-bonding and bonding electron domain. And based on this total of number of electron domain, you predict the geometry of the whole molecule, including the non-bonding electron. And then you remove the non-bonding electron to get the final geometry of the final compound, including only the bonding electron domain. Okay, because I recall in the experimentation, we cannot observe the non-bonding electron, but we can observe only the bonding, that means the bonding electron. Okay. So for example, when you take the molecule of NO2, so you have 3 bonding, 3 electron domain. You have here the bonding, and non-bonding. So finally, nitrogen, you have 3 electron domain. So the arrangement will be the trigonal planar. See here. Okay. So in the perfect geometry, the most optimal geometry, this angle will be 120, and this angle is 120. But now you see that the electron domain surround in this nitrogen. They are not identical. You have one electron domain which is non-bonding. It have one pair of electrons, not bonding. And in other, you have 2 bonding electron domain. So you can see that the interaction between the non-bonding with the bonding will be different compared with the interaction of the 2 bonding electron domain. So as a consequence, you can expect that in reality, this angle will be different at 120 degrees. So the message here is the angle derives from the ideal angle when the surrounding atom and electron domain are not identical. Okay. In say that if you have molecule of BF3, all the atoms surround the boron is fluorized, then in this case, you will have perfect 120 degrees. But for the case of molecule NO2, you have 2 atoms are identical, but you have 1 electron domain, which is non-bonding, which is not identical. So the angle will be derived, that means different compared with 120. The same for the molecule of water here. So the molecule of water, you will have, from the Lewis structure, you will have 1 bonding, 2 bonding. So you have a 2 electron domain, which is bonding, and 2 electron domain, non-bonding. So in total, you have 4 electron domain. Okay. And when you predict the geometry of this molecule, taking the whole bonding and non-bonding, you can say the molecule water can adopt this theta hero. Okay, with the 2 non-bonding and 2 bonding domain. So in the case of perfect theta hero, this angle will be 109.5. But because the 2 non-bonding and 2 bonding are not identical, so in reality, this angle will be different compared with 109.5. So how they will be different is depend on the difference between the interaction of the non-bonding and the non-bonding bonding and the bonding bonding. So imagine that if the interaction between the non-bonding electron domain is stronger, so that means it extends this angle to larger than 109.5. So it also means it forces this angle get smaller than 109.5. So this is what we observe in the experiment. This angle between hydrogen, oxygen, and hydrogen, this one, smaller than 109.5. So this indicates very well that the interaction of the free electron, non-bonding electron, is stronger than the interaction of the bonding electron. It's quite understandable because the electron density in the bonding share between the 2 atoms, making this bond. So you can imagine that this electron are stabilized, taken very well by nuclei of the 2 atoms. So it's quite poor in terms of negative charge. So it can have very weak interaction with the free electron, non-bonding electron. Okay. So now, let's look at one example. Using the valence shell electron pair repulsion model, could you please predict the molecule geometry of O3 and SnCl3 minus 1? Could you please work on that? Maybe because O3 is quite familiar. Could you work on this molecule? SnCl3 minus SnCl3 minus. Anyone can predict the geometry of this compound, please? Little 9. Little 9. Các em có đang nghe thầy giảng đấy?
Yes.
Yes.
Ok.
Yeah.
Có đang thử làm bài tập không? Hay là thôi luôn? Có thử làm không? Thử tí đi cho nó quen tay. Ok. Ok, ok. So, what could be the geometry of this compound? So let's predict the geometry of this compound and also the angle, the value of the angle CL, SN, CL. Okay. Nguyễn Hữu Đức, can you comment, Đức?
Yes.
Yes. What could be the geometry of this compound? Okay, Đức. Nguyễn Thùy Dương. Nguyễn Hoài Anh. Are you here?
Oh, sorry, I haven't done this yet.
Mm-hmm.
Could I attempt this question, Professor?
Yes, please.
So I think SNCl3 would fall into the category of trigonal planar shape,
Mm-hmm.
because the tin here, it will bond with single bonded with 2 Cl atom and double bond with 1.
Mm-hmm. Okay. So what could be, let's we move step by step. First, we need to view the level structure of this compound, right? So what could be the number of valence electron for thin SNs?
That could be 4.
Right? Times 3. And here you have one negative charge and units. So plus 1 equal to 21, 25, 26. Is it correct? So
Yes.
you put SN in the center, chlorides, and the chlorides. You view by the single bond, and then you will have like this. So now you have 8 electron here, 8 electron here, and 8 electron here. So in total, it will have 24 electron already, right?
Oh, I see. So that
So then you will have still have a 2 electron. You put 2 electron here. Okay.
right. So the final shape should be trigonal pyramidal then.
Okay. Why?
Because it bond with 3 chloride atom and have one pair of non-bonding electron, which result in normally a tetrahedral shape, but we do not count the spare bonding, spare non-bonding electron pair. And therefore it form a trigonal pyramidal.
So you see that here you will have 1, 2, 3, 4. So you have a 3 electron domain bonding, right? And you have 1 electron domain non-bonding. You say like this. So we have in total 4 electron bond domain. And 4 electron domain, you will have tetrahedral like this, SN. Okay, so you remove this one. The final compound will have this geometry. So you will have trigonal pyramidal geometry. Okay. So now you understand the step by step to move towards this prediction, right?
Yes.
Okay, thank you. So that's why I invite you guys to practice yourself at home. More you practice, better you faster you can do it. Okay, so now we discussed about the effect of the non-bonding electron on the bond angle. Before I can say that when you have not identical surround electron domain bonding and non-bonding, the angle will be not exactly the optimal angle. You have some derivation. So how is the rest? We briefly discussed already. The interaction between the non-bonding electron will be stronger than the interaction of the bonding electron. So as a consequence, when you have a non-bonding electron domain, this will expand the angle. So it's fourth the angle of the bonding electron domain. So in the case of, for example, if you have perfect CH4 compound, so you have 4 electron domain which are identical. The angle will be perfect 109.5. When you have a molecule Na3, because you have the electron domain of non-bonding electron domain, so the interaction will be stronger. So that means that this, this angle will be larger than 109.5. So this, as a consequence, the angle nitrogen hydrogen will get smaller. And you see that in reality, they observe the angle of 107 degrees. And when you have water with a 2 non-bonding electron domain, the interaction is much stronger. So as a consequence, angle hydrogen, oxygen, hydrogen gets even smaller. So the real angle that's they observe in the crystal, water crystal, is 104.5 degrees. Okay, so the take-home message is the non-bonding electron
Professor, we can't hear you.
pair. Can you hear me now better?
Yes.
Okay.
Okay, thank you.
Yes, we can
Thank
hear you
you.
now.
Okay, now we discussed about the effect of the multiple bond and on the bond angle. So for example, here you have in this molecule, you have a double bond here, and you have a single bond here. Okay, so you can see that this you have a not identical bonding, not identical electron domain. So you can expect also this bonding are different than the perfect 120 degree, right? So because when you have a double bond, that means you have a single bond and a second bond. Later we understand that the p bond. And you also understand that this bond normally is shorter than the single bond. So as a consequence, you can imagine the electron density here in the double bond higher than the electron density in the single bond. Does that mean the interaction of the higher electron density will be stronger than the interaction of the smaller electron density? So what make as a result? The interaction of the double bond and the single bond will be stronger than the interaction of the single bond and single bond. And the consequence, this angle will be larger than 120 degrees. So as reality, you observe 124.3 degrees for this case. And as a consequence, the angle between the chlorides, carbon, and chlorides will be smaller than 120. So in the experiment, they observed 110, 111.4. So the take-home message is electron domain in the multiple bond exerts a greater repulsive force than the single bond. Is the one you can remember is the double bond have a higher electron density. The triple bond have an even higher electron density than the double bond. So higher electron density have a higher negative charge. So the interaction, of course, will be stronger than the single bond which have lower electron density. That's something you can remember, you can understand very well. So you don't need to remember too much things. Okay? Now, you have some special case. You have a nitrate ion. So here, by looking at this level structure, you understand that you have a single bond, you have double bond. So by remembering the two masses in the previous slide, we understand that the interaction of this double bond with the single bond will be stronger than the interaction between the two single bonds. So you can expect this angle larger than 120 degrees and this angle smaller than 120. That's what you expect. But in the experimentation, so they figure out that this angle are perfectly 120. Okay. So can you explain why that? Why the angle here is perfect 120, but not like we just discussed about the different interaction of the double bond and the single bond electron? Anyone can comment?
Maybe because this ion has a resonance structure and therefore all bond strength are the same.
Yes, thank you. Actually, because in this case, we need to consider the resonance structure. We cannot, in the resonance structure, we can imagine that this double bond will be resonate to this position and also resonate to this position as well. So basically, we cannot distinguish the three oxygen, 1, 2, and 3. They are perfectly identical. And the bond angle are perfectly identical. So they have no difference between the three oxygen, and as a consequence, the real angle here is perfect 120 degrees Celsius. So when we have already the geometry, we need to consider also about the resonance structure to see the different possibility. If they have resonance structure, it's very likely that they will have identical atom. So identical atom, that means the electron domain around the central atom will be identical. So in that case, they will fall in the perfect geometry which have identical angle for the different bond. Okay. Now, we talk about the central atom which follow the octet rule. That means they have maximum 8 electrons in the valence cell. That's correct for the first and the second row of element in the periodic table of element. When you move to the third rows, you start to have orbital D in the atom. And when you have orbital D, you understand that the outermost layer, so the cell, the outer cell, will have subcell S, subcell P, and subcell D. You have 1S, 3B, 5D. So in total, you have 9 orbitals. And with 9 orbitals, you can accumulate, you can receive up to 18 electrons. So you can have a central atom which make the chemical bonding, which have higher, more than 8 valence electrons. So in the case of S more than 8 valence electron, the geometry will be go further than the theta hero. Okay, theta hero, that means you have a 4 covalent bond, identical. But if you have a more than 8 electron, you can have a more than 4 covalent bond. So in that case, you go to the geometry more complicated than the theta hero. So here you have the case. You look at the case of one molecule with 5 covalent bond. So in the case of 5 covalent bond, you will see this structure by pyramidal. Okay, so because each of this is one pyramid, so you have 2 pyramids like this. Okay, so in that case, you have 2 categories of the bonding. One in this X, you have axial position. Okay, and so you can have Z, and then you have other category of the chemical bonding make up this 1, 2, and 3 bond. You have equatorial position. Because when you make the connection, it look like equator in the on the planet. So we call the equatorial position, and the position in the X perpendicular with the equatorial plane, we call the axial position. So now, if a molecule have a non-bonding electron domain, they will occupy the equatorial position. That means if you have one molecule with this geometry, and you have non-bonding electron domain, so they will occupy this position, and this position, but not in axial position. Okay. Let's say, take the case. Imagine that you have one compound with one non-bonding electron domain. So you have one atom, 2 atom, 3 atom already, right? And then you have one non-bonding electron domain and another atom. So you have 2 possibility. One possibility, you put the pair of electron non-bonding here. So the possibility 1. And then you have other possibility, you put the electron here, you have the second electron possibility. Now, it doesn't matter non-bonding or not non-bonding electron. You need to arise to the geometry where the molecule have most stable state. It means it will be at the lowest potential energy, most stable. It also means you need to arrange non-bonding electron pair to make the interaction optimum. So imagine that if you put the non-bonding electron in the option 2, that means in axial position, so we will have the atom here in this position. You see that this non-bonding electron will have very close interaction with 1, 2, and 3, and this angle is 90 degrees. So that means that the non-bonding pair electron have very strong interaction with the 3 ligand. Now, if you take the second option, you put the pair of electron non-bonding here, and then the atom here. So you see that 2 atoms have far interaction, weak interaction, because the distance here is 100 degrees. So the distance is quite far. So among the 4 ligand, 4 atoms, you have you have 2 strong interaction due to the 90 degrees of the pair electron with this one and this one. So you have two interaction through 90 degrees and two interaction through 120 degrees. Okay. For the case of the first option, you will have three interaction 90 degrees and one interaction 180 degrees. Through the angle of 90 degrees will be very strong because the distance is short. So it's less stable. So you say that when the electron put in the axial position, it will be less stable than when you put in the equatorial position. So that's why if a molecule have a non-bonding electron pair, they will occupy the equatorial position. Okay. It's quite easy to understand, I guess, right?
Yes.
So here is summarized a little bit different electron domain around a central atom. For example, when you have the molecule with the T shape, you have two electron domain in the equatorial position. When you have a linear compound, but actually the central atom have d orbital, and you have a three non-bonding domain, not non-bonding electron domain position in the three different equatorial position. The same for this one is not very important. So in the case you have larger molecules, this molecule is still very small, acidic acid is quite small, but larger than the CH4. So we first look at the interior atom, that means the central atom. Here, in this case, you will have of carbon, and oxygen. So instead of looking at the geometry of the whole molecule, we should look for the geometry of X interior atom, carbon, oxygen. So you can predict the geometry for X of the atom individually. Okay. So here you go. You can see that this carbon interior surrounded by three hydrogen and one carbon, you will have a geometry of tetrahedral. So you can predict the bond angle of 109.5. And then this carbon, you have a trigonal planar with predicted angle of 120. And the third atom, the oxygen here, you have 1 and 2 non-bonding electron domain. So it will have tetrahedral geometry and also the angle close to 109.5. Okay, so the message is that you divide, if you want, the large molecule into different
Professor, we can't hear you.
Okay, it's now better?
Yes, yes.
Okay. So now we talk about the geometry, the shape of molecule. Now we talk about the dipole moment of the molecule. So the dipole moment of the molecule depend on both the polarity of the individual bond and the geometry of the molecule. So in previous lecture, we know already about the bond dipole, the dipole moment of the chemical bond. Is due to the moment of only two atoms in that bond. For example, you have the molecule of CO2. So the oxygen have higher electronegativity than the carbon. So you have the dipole moment like this one. So it say that the carbon oxygen single bond is polar. But in this camber of CO2, you have two identical CO2. So you can represent the dipole moment by a vector like this. Huh? So you put the positive charge and the negative charge like this one. Negative charge for the higher electronegative element and the positive charge for the lower electronegative element. So you have one vector like this one. You have a second vector like this. So the total dipole moment of this molecule would be the addition of the combination of the two vector. So you can see that for this molecule, because it's linear, so the two vectors are exactly identical, but they are in the opposite direction. So the combination of these two vectors will be 0. That's why the molecule of CO2 is quite special. Its chemical bond inside is polar, but the whole molecule is non-polar. If you do the same thing for the molecule of water, so you have positive like this, negative, positive. So you have the first vector, and then you have the second vector. So you can do like this one. So you do the combination of vector. So you have this final vector result, which is the dipole moment of the whole molecule. So you see that for the molecule of water, because the geometry is not linear but bend, so the two vectors make an angle different than 180. So finally, the combination of these vectors is different than 0. So the molecule of water is polar, while the molecule of CO2 is non-polar. Okay. So to identify the dipole moment of the molecule, first you need to identify the vector present the dipole moment of the single bond, and then you do the combination of the vector. The result will be the dipole moment of the whole molecule. Okay. So here, for example, if you have molecule by atom, hydrogen and chloride, it's quite easy. If the two atoms are identical, so the vector equals to 0. So you have a non-polar compound. If you have two atoms which are not identical, then you have a polar compound. For the bimolar molecule, by atom molecule, it's quite easy. But when you have more than two atoms, then you need to look at the geometry of this compound. For the case of the BF3, for example, this angle is 120 degrees. So when you do the combination of this vector, the two vector, you see here. So here is going to be 60, right? So this vector combination of these two vectors will be exactly identical to this one. So it means this vector will be also identical to this one, but they are in the opposite direction. So the combination, the final combination of this and this will be equal to 0. So that's why the dipole moment of this one equal to 0, and this compound is non-polar. The same for this molecule of CCl4, but when for the case of Na3, you make a combination, you will see that's the final vector will be different than 0. So you have a polar compound. For the CH3Cl, also you have a polar compound. Okay, so this is quite simple. First, you need to identify the vector represent the polarity of the single bond, and then you do the combination of vector. You do the vector combination. Okay. Now we end by this slide. Here you have a molecule, famous one, especially in Vietnam, curcumin. This curcumin molecule is presented like antioxidant molecule that can be very helpful for patients who are sufferers of, like say, cancer and so on. So a lot of positive application has been presented. We are not talking about the application, but here in this lecture, when you know about this structure, when you know about the molecule structure of this compound, can you predict what could be the polarity of this compound? And do you think that this compound will be soluble in water? If it's soluble in water, and why? If it's not soluble in water, then why? And in the case it's not soluble in water, how can we improve the solubility of this compound? Anyone can comment on these three questions? Maybe I propose that we have 5 minutes break. During the break, we can think about this one, and then we'll be back. We discuss on this question before we move to the second part. We talk about the overlap of orbital to make the chemical bond. Okay.
Okay.
Okay. Thank you. Okay, so can we come back and continue our lecture?
Yes.
Okay, so anyone have idea about the polarity and solubility of this compound curcumin in water? First, do you think that this compound is polar?
I think curcumin is non-polar.
So what could be the polar, the solubility in water?
So it will be not soluble in water or maybe very little soluble.
Then the last question, how can we make it more soluble in water? It is not soluble. How can we make it more soluble in water?
I think we should add some substance to make the water become like an emulsion solute. I think so. So it will be more. So curcumin will be more soluble in water.
So this is very interesting question because people prepare as a powerful substance. That's very good for this can be presented as an antioxidant compound. But then when it's put in our body, it should be soluble because our body contains a huge amount of water. So we need to look at the polarity of this compound. At the molecular level, we can see that you have some polar bond, carbon oxygen, carbon oxygen. You can have also oxygen hydrogen, which is the polar. But the number of the non-polar bond, like carbon-carbon, here is huge, and this molecule is quite big. So if you put the polar bond like a vector and you do the calculation, you can see if you do the combination of the vector, you can see that finally this molecule have polarity. It's polar, but the polarity is very small. That means the dipole moment of this compound is very small. So it says that this compound can be dissolved in water, but not a huge amount. In other words, the solubility of the curcumin in water is very low. How we can improve the solubility of curcumin in water? If you take a pure water, you take a pure curcumin, you cannot change the polarity. The polarity of curcumin, you cannot change. If you water, take a pure curcumin, the fixed, right? You
So we can't hear you.
put curcumin in one medium which have more polar, so dissolve better in water. Is other engineering fact. But what I want to say here is that if you consider about the pure curcumin at the molecule, then the solubility in pure water is extremely low. Okay, so and then you cannot change the polarity of the curcumin. You can change, you can do some substitution, but you cannot change hugely the polarity of the molecule. You cannot change the polarity of the pure water. So what you can change is that you modify water, you put some substance that make the mixture with the polarity lower, or you can put curcumin in some environment which have higher polarity. Okay. Now, let's move to the orbital overlap. So we talk about the valence bond theory. Let's say the idea is quite simple as following. In a covalent bond, we say that bonding is built through the sharing electron, valence electron of the atom. So the electron valence electron look like in the atomic orbital. That means in the orbital of X atom. We are talking about the valence electron. Huh? So the two atoms get closer. When they approach each other at some distance, being very close to the van der Waals distance, they start to have overlapping of the atomic orbital. And then the overlapping progress to optimize all the different interaction. What could be the different interaction that should be optimized? You have first one nuclei which is positive, another nuclei which is positive. And you have orbital. So you have electron negative here and another electron negative here. So when the two atoms get close each other, the electron from this atom will be attracted by the nuclei of the second atom, and inverse, the electron of the second atom will be attracted by the nuclei of the third atom. So that is attractive force will make the two atoms get closer. And then, but they cannot get closer infinitively, because when they get close enough, the electron from this atom and the electron from this atom have repulsive force because they have the same negative charge. And also the interaction between the two nuclei, both are positive charge, also are repulsive interaction. So the two atoms get close at the point they maximize the attractive force and minimize the repulsive force. So they will reach an equilibrium between the attractive and repulsive force. At that equilibrium, it will have the overlap of the two orbitals reaching the maximum overlapping, and you create the chemical bond. So by this idea, this concept, you can imagine the overlapping of the two orbital 2s. So you have an overlap region here. The overlap region will be on the line linking the two nuclei of the two atoms. If you take one orbital s and one orbital p, you can see the overlap by this way. Because here you have high electron density, but you cannot have overlap at this position, because here at this position, the electron density in the orbital b is low. So you cannot have a good probability to find electron there. So there are no overlapping at this position. As another overlap, you can see between the orbital b and orbital b. It's the same for the orbital d if you want. So you have orbital d like this one. So you can have orbital d like this. So you can have also the overlap between d and d. Okay. Of course, the orbital d will have another mode of overlap like this one. You will see. You will have another. So you will have also dd. So this one make a sigma bond, and this one make a p bond. We will see later, but just for information for now. So the idea is that the two atomic orbital approach, when two atoms approach, and then they can overlap to optimize the interaction, attractive and explosive interaction, so create the chemical bond. Now, this diagram is one of the most important one in the general chemistry, And it will go with you in the inorganic chemistry, it will go with you in the physical chemistry, and so on. One of the key diagram. What does it mean? When you look at this diagram, what you can learn? When the two atoms get very far from each other, there's no interaction. So they are two individual, two separate atoms. Then the total energy of the two will be equal to the in combination, the sum of energy of the two atoms, right? So that means they will have no tendency to be in the interaction, in the bonding. You can imagine that one thing important of the concept I would like to share with you here. When the two atoms are free, they are separately, they are free, so they have high freedom. And the parameter describing the freedom of the system we call entropy. I mean, they are free, they can move, they can do whatever they want. Now, if they go together, they create the combination, they create the bonding. So they lost their freedom, right? When one atom moves in this direction, the second atom should follow because they bind together, okay? They have one chemical bond between. So that means they lost their freedom. So in return, because they lost freedom, they need to gain something. If you lost the freedom, but you will not gain something, you are not likely to accept this bonding, right? When they lost the freedom, they should gain in terms of energy. How they gain energy? That means the total energy in the chemical bonding should be lower than the total energy when they are free, they are individual, free, before bonding. So with this concept, you can understand that when the two atoms move from the individual to the start to overlap, that means start to bond each other, then the total energy you will see here is get lower. So that means when you have a potential energy, you have a two atom individual, higher energy, and then when they start to overlap, they will go lower. So you gain this term of energy. Okay, so here you go from the individual to here, you gain this amount of energy. When the atom gets closer and optimal, it makes higher overlapping, the energy further decrease. So you decrease in the potential, and at the distance which is the optimum, that means you create a stable bond, the energy here will be the lowest one. So here you gain the huge amount of energy compare when with the case when the two atoms are separately, freely individual. So you can see that when they create the bonding with the distance very short, here you can see in the case of hydrogen bond is 0.7 angstrom, very short. That means the two atoms get very close to each other. They lost freedom that they have when they are individual, but they gain in terms of energy. So that is the price for making the chemical bond. So when you make the chemical bond, you gain in terms of potential energy, your system make more stable, but you lost in terms of freedom. Okay. It's quite easy to understand in our life. When you team up with someone, you lost the freedom because when you work in team, you need to follow the team leader. You need to share work with other team members. So whenever you want, you do whatever you want. when you do what style you want, present or PPT, BDF, or whatever you want. But when you are in team, you need to follow the team leader. You need to share the task with your team group. Sometimes you need to share one other team member, the easiest one, and you need to work in the hard task. So basically, when you are in the teamwork, you lost your freedom. But what you can learn? You learn expertise from the other member, and you can solve the whole problem without yourself need to solve the whole task. So that means you gain in terms of efficiency. So if you are in the teamwork, you lost the freedom, but you cannot gain the quality and the efficiency of the work. Of course, it will not accept to be a member of that team. So the same for the atom. When they bind together to make the chemical bond, they lost in terms of freedom, lost entropy. They cannot move freely, easily, but they gain in terms of energy. So when the covalent bond breaks the bond distance, that means the most stable state, the energy will gain maximum value, and thus represent for the stability of the covalent bond. Okay, now all of the chemical bond, anyone, not only hydrogen bond you see here, you can describe by this diagram. That means when I give you one molecule, A, then you understand that's the molecule AA is in this potential energy here. It's not only one unique value. It is in the most stable state, we call the ground state. Okay, the most stable one. But in reality, when I give you one molecule with the ground state, this one, it's not only this unique value that you should imagine. You should imagine that it's here, the molecule here, because it is in the bottom of one diagram like this. So what you can understand from the diagram? The molecule is stable here. They give you one molecule, it's stable here. But it can take this also state. It can take also this state, this state, this state. Okay? What difference between the ground state and this state? Actually, it's different in the distance between A and A. That means when you move from the ground state to this state, the second one, we call the second, third, fourth, five, and so on. When you move from the first state, the ground state, most stable one, to the second one, basically you make the chemical bond longer. Okay, the distance between the two atoms get longer. When you move to the third one, the third state, the distance even get longer. Move to the fourth state, get longer. Five state, get longer. And when you move to here, the end state, then the distance will be too far to be considered like a chemical bond. That means it breaks this chemical bond. Okay? So if you have the capability to bring one molecule, one chemical bond from this state, ground state, to this one, actually it breaks the molecule. Okay? Now, if you have the compound A, you mix in the chemical reaction to get the compound B. Okay? So, in very simple diagram, I show you, you have energy, you have AA here, and you have BB here, right? So the process will be is if you drive by this way, it looks like the process is direct from AA to BB. And you say that the process is downhill, that means exothermic is happens spontaneously. And when the reaction happens spontaneously, why you need to put energy to activate it? By this diagram, is very difficult to imagine. But now, if you imagine that this diagram can be understood like this one. Huh? So you change from the compound AA here. But the reaction happened. You should imagine that you have a compound AA here at the ground state. To move to AB or to move to BB, you need to bring this AA from this ground state to this position. That means the cross section, the cross point between the diagram of AA and diagram of BB. So when AA go to this position, you have two possibilities. It's been flown back to the initial AA, or it's been flown to the product BB. So you imagine that now you need to put energy inside because of this energy gap you need to bring from the ground state to here. So you bring here to this first state before it's flown to the position of B here. Okay? So now you understand the energy that you can measure at the end of reaction represent only the difference AA at the ground state and BP at the ground state. It's not represent the real situation where AA needs to be destabilized, bring it up to this position before it can fall to a second curve to become product. Am I clear in my explanation?
Yes, but
Okay.
I have another question.
Yes.
Okay, so what if we provide more energy than it's needed to reach, for example, the fourth stage? Would it fall to the BB state or it falls back to the AA?
Okay. If you put more than the energy you need, right? So the reaction fall further to the B. It will not be back to the A. Okay.
Okay, thank you.
Because when you put more energy, that means you provide more population of A to the first state. That's the case. Because when you talk about AA to BB, we are talking about one single AA and one single BB. But in the reaction, you have a population of N mole of AA, right? So when you put more energy, that means you bring more population of AA to this excited state and it falls down. Okay? Now, the second image of this figure is also, you have a bonding, covalent bonding. You have a compound AA here. Huh? What we can learn from here? We learn that if by somehow you move from AA to this position, let's say first state, then you get the distance from AA, the two nuclei, gets longer. And when you learn about the chemical bonding, you understand longer bond, that means weaker, right? So by doing so, it means that you have input energy to bring from the ground state to the first state and make the bonding between AA get weaker. Okay. In other words, if you want to destabilize a chemical bond, that means you make it weaker. You need to put energy in to excite from the ground state to the excited state. Okay. So if you take one molecule, you do not do anything, you do not put any energy into the system will be stable because it is in the ground state. It's in the bottom of energy curve. Okay. Now, we move to the next concept. We talk about the hybrid orbital. So in the here you see in this slide summarize of the two concepts we already learned: the valence shell electron pair representation model and the valence bond theory go through the overlapping of the atomic orbital. So the valence shell electron pair representation based on the electron domain representation force, so including both the bonding and non-bonding electron domain, is forget the atomic orbital. We consider only about the electron domain. We forget about the orbital. That means electron domain of orbital of electron domain S or electron domain P, they will not comment, but they can consider S and B will have the same character for this model. We consider only about the electron, not the original orbital, that means S, B, or D. The good point of this model is that we can predict the molecular geometry. When we first start by the Lewis structure, you calculate the number of the electron domain. You can predict the geometry of the whole molecule if we include both bonding and non-bonding domain, and then we remove the non-bonding domain, non-bonding electron domain. So you have the final, you have final prediction of the molecule. That's a good point. About the valence bond theory, based on the overlap of the orbital, so it's based on the atomic orbital shape. That means we can say the overlap of the orbital S and B will be less easier if we take the two orbital S, because you can see that the orbital S have a very high symmetry. All the direction will be the same. For the orbital B, you have a precise direction. So here in this figure, you see the overlap of S and B. So it goes from S, any side of orbital S can be overlapped, but only the heat of the orbital B can be overlapped. So now if you take two orbital S, you take any direction, they can overlap easily. Now, later, if you have a two orbital B, you can have a heat to heat or back side by side overlapping, but not all the directions. That means you have only two possibilities of overlapping. So that means the overlap of the orbital depends strongly on the shape of atomic orbital, because it's linked with the direction of overlap. That means it's linked with the symmetry of orbital. But the problem is that by simply following strictly the valence bond theory through the orbital overlap, we cannot explain experimental observation. What could be the experimental observation? We cannot explain. For example, when you take the carbon, you have a 4 valence electron, right? Then you have 2 electrons in 2s, and then 2 electrons in 2p, like this. Okay? And because when we talk about the overlap, we consider about the shape, the origin of the atomic orbital. Then we can understand that when the carbon make the chemical bond, the 2 electrons in the orbital s will have overlap differently compared with the 2 electrons in the orbital b. That's the first thing. It say if you take the carbon and you make the molecule of let's say 2, you can say that 1s of hydrogen will overlap with the 2s of the carbon, and another s of hydrogen will overlap with the 2p of the carbon. And then the 2 carbon hydrogen bond will be totally different, because the overlap will be different between S and Sp will be different. But it's not the case. The molecule Ca2, later we know very well that the 2 carbon hydrogen are exactly identical. So by using the valence bond theory based on the orbital overlap, we can explain the case of Ca2. That means experimentation, something strange. The second one is that now, based on the overlap, that means the orbital B here, which has empty, there's no electron, then you cannot imagine that it can create another bonding, because when you have an overlap orbit with other orbital, that means you need to have one orbital have electron density, not zero electron density. So it means by following this theory, we can imagine that the carbon can create maximum 3 orbital overlaps. That means maximum 3 valence bond, 3 covalent bond. But in reality, in experimentation, you have the molecule CH4. So in the molecule of CH4, all the carbon hydrogen are identical. So that means this theory, overlap orbital, need to modify, need to be developed a little bit more to explain the experimentation. So with this demand of adapting the theory to explain the experiment, they came out with the idea of hybrid orbital. So the hybrid orbital explain the observed orbital in the covalent bond, and it's worked very well for the carbon compound. And normally, this hybrid orbital are frequently used in organic chemistry. Okay, so I hope that I already convincing. I can convince you why the hybrid orbital need to be developed, not just for fun, not for fun. Develop theory for fun, but we develop theory to explain better the experimentation. Thus, the previous theory cannot fully explain. So now we look a little bit about the hybrid orbital. Let's say take the case of PS2. So the baryon's electron configuration is following. So you have ground state. When it have the excited state, one electron will move to the orbital B, and then you have a combination of the 1s and 1b. You create 2 orbital sp. Okay, so it looks like you have one orbital s. You take 2 orbital b. You create. You take 1 orbital b. You create the 2 orbital sp. So the orbital sp we call the hybrid orbital because it's result of combination of the orbital s and orbital b. And hybrid orbital have both character of orbital s and character of orbital b. So the sp here you see. Oops. Okay, so the orbital sp here have character of orbital s. Sorry, have a character. And it have a character of orbital s. The orbital s have very high spherical shape, and it have high symmetric. So basically, you have an S domain because in this area you have very high domain, the domain with a high symmetry. Bigger is look close to the orbital S. So that's why we say that the hybrid orbital sp have a both character of orbital S and character of orbital B. So then you take the hybrid orbital, 2 hybrid orbital to overlap with 2 orbital s of 2 orbital b, sorry, of the f fluoride. So you create 1 sp hybrid and 1 p orbital to create 1 single bond. So in total, with 2 hybrid orbital and 2 orbital b from 2 atoms of fluoride, you create 2 single bond. You can have several, you can have a different mixture, combination of orbital S and B. So we talk about the case when you have a one S orbital and one P orbital. You can have also the combination of one S orbital with two B orbital. You can have also one S orbital with three B orbital. Have now in terms of energy, you have orbital S have a lower energy than the orbital B. So when you recombine, the hybrid orbital will have energy say that when you have sp hybrids and sp2, the sp have higher s character than sp2, and the sp2 have higher character b than the sp. It means the percentage of the combination more in s for the case of sp and more in b for the case of sp2. That means the hybrid orbital sb will have a higher symmetry compared with the sp2, right? That's the meaning. You have more character of s, so that means the symmetry higher. You have more p, that means you have a less symmetry. It's important because when we talk about symmetry, the bonding can come from different directions. So that means you have more possibility to overlap with other atomic orbital. Okay. So here, the case you have a 1s with 2p. So you have what we call the linear combination. That means 1 plus 2 equal to 3. Crazy mathematics for the chemistry. We never go more than 10. 1 plus 2 equal to 3. 1 plus 3 equal to 4. So that we call a linear combination. So you have 1s and 2p. You have a 3 orbital sp2. And 3 orbital sp2, sp2 is will have more character of the p, so you see that it will arrange in 3 directions. So here you put together, you have a system of 3 sp2 hybrid orbital. It can, if you put together, it can range in the 3 direction with the angle of 120 degrees. So you can make a 3 covalent bond easily. If you put in 1s and 3b, you have in total 4 hybrid orbital at p3 and 4 orbital. When they arrange in the 3D dimension, 3-dimension spherical coordination, you will have a theta hero. So with the angle of 109.5. So that explains why you have a theta hero geometry for the molecule of CH4. Now, how we can predict the hybrid orbital? First, you need to draw the Lewis structure of the molecule or the ion under the consideration. You determine the electron domain geometry using the valence shell electron pair repulsion model. And then you specify hybrid orbital for the bonding electron pair based on their geometrical arrangement. So for example, take the case of Na3. First, you draw the Lewis structure, and then you know that the nitrogen atom will have 4 electron domain. So you arrange in the 4 electron domain geometry. So that means nitrogen need to have the sp3 hybridization. That means 1s, 3b to satisfy the 4 electron domain. Okay. Okay, so here summarize quickly the atomic orbital says, hybrid orbital says, geometry, and few examples of the molecules that have this geometry and have this hybridization orbital. So if you take the orbital set of 1s, 1p, you have a 2 orbital hybrid orbital sp, and the geometry of molecule will be linear And for example, you have BF2 mercury chloride. You have SB2 for the molecule like BF3, SO3. You have SB3 for molecule like CH4, Na3, water, ammonium, cast iron. We can go for also for the K of the central atom have a more than 8 electron. So we put set of S have 5 and 5 orbital sp3d with arranged and in the p pyramidal geometry. And then you will have the molecule of BF5, SF4, B bromide fluoride. You can make also 6 hybrid orbital sp3d2. You see very linear combination. It's addition. So you have octahedral geometry. The famous one is SF6, right? The sulfur is in the third rows of element, so it's have an orbital d. It's not possible for oxygen because oxygen is in the second row. Okay, that's we talk about the single bond. So we talk about the sigma bond. Now we move to the multiple bond. So a sigma bond is a bond in which the shared electron density is concentrated directly along the internuclear axis between the two nuclei involved in the bonding. So that means, very simple, the electron density, the shared electron density here, if you take the nuclei, you draw the line, so the shared electron density is along the internuclear axis. That means in between the line. Okay, so for the same, the nuclei, you make a line like this, so the shared electron is here in between on the line. Okay, so that is the sigma bond. Huh? Now you have the second concept of p bond, that's formed from the side away overlap of the p orbital, resulting in the region of electron density that are concentrated above and below the plane of the molecule. So let's say you have the orbital B overlap, that we call the sideway overlap, like this. So the electron density generated from this overlap is go above the internuclear axis that connect the nuclear of the two atoms and below. In the case of sigma is in between, but now in the case of p bond is above and below. That's for the case of the b orbital. But for the d orbital, you can do the same thing. Let's say the d orbital, you can have this. So in that case, you have two nuclei and you have an overlap in between. So here you have sigma dd. But you can have also in this case, so you have the side overlap, and if you take the nuclei, the line in the nuclear, then the overlap will be above and below. So that means here you have PDD. Okay. So the message is the p orbital, the p bond can be generated from the b orbital, but can be also generated from the d orbital. You can have also the case when you have the d orbital like this, and you have a b orbital like this one. So you have intranuclear basis, and you have a string above and below. So here you have a p bond, d and p orbital. Okay, so you see that the not only pp can generate the p bond, but orbital d can also make it happen. Okay, so for the case of multiple bond, you can have one single bond, which is sigma. If you have a double bond, you have one sigma bond and one p bond. When you have a one triple bond, you have one sigma and two p bond. So it's quite easy to understand. So here, the case of double bond in the C2H4. So in the case of C2H4, you have a hybridization sp2, and so you have one sigma bond, and then you have one p bond making of the orbital p. For the case of the triple bond, then you have the case of C2H2, very classical one. So we have hybridization of sp, and then you have two orbital b can be overlapped by sideways, and then you have a two p bond. Now, in the case of resonance structure, so you can see that for the case of C6H6, the benzene, you have the sigma bond between the carbon and carbon. You have sigma bond between carbon and carbon like this. And then you have a p orbital that can make the p bond like this one, p bond like this one, p bond like this one. But also you can make the p bond like this way, and this way. So by the concept of resonance, we say that the p bond will move from this one to this one to this one to this one and to this one. In other words, we can say that all the orbital b will overlap and make a cloud together above and the bottom of this molecule plane. Okay, so basically we cannot distinguish the carbon atom. So here, so you see the localized structure of the p bond. That means the p bond localized on the two carbon, and then you switch this that bond to here, this to here, and this to here. So you have the second resonance structure. And if you put all together, basically, then you have what we now we discuss. They have a resonance structure, and the p bond will be delocalized over three oxygen atoms. That's why the three oxygen atoms are exactly identical, because of the localized. Whether one oxygen will have a higher p electron than the other one. Now, take the case of this compound, benzene. So, one then, and then another one, like this one. Can do like this, like this one. Like this. Due to a delocalized. If you take the diamond, then the carbon will be like this. And then the second carbon will be also like this. The carbon here is sp3, and all the carbon here is sp2. So what you can see? You can see that If imagine you inject electron here, so it looks like you inject electron in this position. In this position, let's say you make electrical contact. Yeah, okay. You inject electron to this carbon position, but because of delocalized bond, the electron will flow very quickly to this position. Okay, so imagine that you move from one single C6 cycle to the condensed cycle of the graphene. You put electron from this position, it's quickly the electron will move to this position. So if you make contact here and contact here, you can see that the electron will move quickly from this point of contact to this point of contact. So that explains why the graphene have high electrical conductivity. Why for the case of diamond, you have own sp3 like this and own a sigma bond. You don't have this delocalized B bond structure. So that's why if you put the electrical contact here, you put the electron here, it takes very huge difficulty to make the electron get out from this position, another carbon like this. So that's why diamond is not conducting. So you see that if you take the same element, but you put in the different chemical bond, different geometry, different bonding mode, you can display totally different physical and chemical properties. One case, like for the graphene, thanks to the delocalized p bond, you will have an excellent electron conductivity. In another hand, you have a perfect structure of the diamond, which have no conductivity because all the bond inside is sigma bond with the hybridization sp3. Am I clear in this point? Hello.
Hello.
Yes. Can
Yes.
you do you understand what I mean? No.
You can say again.
Okay. In short, we are describing about the B bonding, right? And then in the case of resonance structure, by very simple look, we can distinguish the B bonding from localized bond for two carbon in this case, and two carbon in this case. It looks like you have a double bond here. Let's say you have C1, C2, C3, C4, 5, and 6. So you have a double bond C1, C6. And then here you have the double bond move from C1, C6 to C1, C2. It looks like a movement, okay? That's something we can imagine by using the localized B bond. But in reality, what I say is that all the B bond will be delocalized. That means it's equally distributed over all the carbon sp2 of the benzene. So all of the carbon will link together through the sideways mode P bond of the orbital P. So thanks to this resonance, thanks to this delocalization, that means that if you have electron density inject here, you inject electron in the carbon number 6, it will quickly move to the carbon number 3 here. If you take this case of carbon, the localized B bond, let's say you inject from the number 6, it can move to the carbon number 1, but it cannot go to the number 3, right? But in reality, because all go together in a resonance structure, is a delocalization. Sorry. So when you inject electron in carbon number 6, it will quickly move to the carbon number 3. This easy to understand, okay? Yes.
Yes.
Okay. Then if you extend the concept not only for C6, but for the C6N, that means you use N time of the benzene rings and you put together in the structure of one material we call graphene. So graphene have this structure of C6 N time. So the concept will be the same. You have orbital B, which will be delocalized from the atom number 1 to the atom carbon number N. So that means now, if you inject electron, the electrical current is electron current, okay? If you inject electron in the carbon number 1, it will get escape from the carbon number N very quickly. So that means, thanks to this delocalization, the graphene have excellent electrical conductivity because the electron movement is free. Thus, you can understand, right? Căng nhờ. Cứ mở rộng một tí là lại khó khăn thế này à? Hả? Còn nếu mà cứ học mấy cái bonding này thì có cái gì để học đâu? Hả? Okay. Okay, so try to understand it, try to have self-learning in this point later at home, right? You see that in my class, I try to bring you the actual exam that is ongoing in the research and development. Thus, we can play something, we can, how to say, we can earn money, we can make money from this. Only the textbook of benzene, of the resonance structure, okay, you can get 20/20 in the examination. But then after that, what will happen? There's no added value in the lecture. So, I mean, the fundamental information, fundamental clothes are important. You try to understand it. But understand the concept is not good enough for students at the university and far from enough for the student at the science and technology university like USAS. Let's say one of the big problem now is graphene, a system of benzene rings. You put together a lot of benzene rings, then you have graphene. You see that benzene is nonpolar, right? So it's not soluble in water. Is it clear, right? So when you extend from benzene to graphene, that means from one single ring of 6 carbon to 600, 6,000 atoms of carbon, the molecule is still non-polar and it's not soluble in water. However, as I explained, because of delocalization of p bond, the benzene have quick movement, electron communication between the carbon numbers 1 and carbon number 6. When you extend to the carbon 600 and 6,000 graphene, the communication, the interaction, the communication in terms of electron communication between the carbon number 1 and carbon number 6,000 is also excellent. That's why the graphene have excellent electrical conductivity. However, it have no good solubility in water. So you cannot manipulate in industry. If you want to manipulate in the industry, let's say you disperse graphene in one solvent, you make a thin film of one graphene to make excellent electrical conductor. But before you can make it, you need to disperse graphene in water. But it's not soluble in water, so how you can make it? So you have one side very high electrical conductivity, and on the other side, dark side is low solubility in water. So some people say that, okay, understand. Now I have the graphene mixed from benzene. It's not polar, so I need to introduce some polar compound, some polar function in the graphene. So for example, I put here COOH. So it's become polar. But the problem is that when you have carbon like this, okay, you have own carbon, sorry, oof, like this, own carbon sp2, okay? But when you want to create COOS, that means you introduce one COOS here, that means this carbon become sp3. And when you have sp3, that means this position is no longer resonant. That means the p electron cannot delocalize in this position. So more COOH you introduce, higher solubility of graphene is, however, lower conductivity is. So if you want to earn money, if you want to make money with your technology, you need to identify an optimal number of COOH to have a excellent solubility, at the same time have excellent electrical conductivity, which is extremely difficult. You get what I mean?
Yes.
Okay. Hope so. Okay. Let's say try to learn the textbook through the inspiring or interesting problem, rather than understand, remember, having examination and forget. Right? We are now at the university. After graduation at university, you have nothing to learn more. Of course, you can learn master and PhD, but not all of you will do that. Most of you need to graduate and do something in the industry, contribute in the development industry. So the preparation of university is for the future job in the market, not for 20 over 20 in my class, right? You see that the examination is quite simple, very easy. But what I invite you guys, please take the chance of learning general chemistry like the way to understand the ongoing problem and how we can think about this one day when we graduate. Okay, I hope that my message is clear, and hope that some of you will share my opinion. Okay. Okay. So now we still have 20 minutes. We will have half an hour to discuss on very important topic, which is molecular orbital. So we start by the fact that the valence bond theory and hybrid orbital are not good enough to describe the excited states of molecule. They are excellent to describe the ground states of molecule, but not excited state first. So that's why the chemists developed the molecular orbital theory to describe the electron in the molecule by using specific wave function we call molecular orbital, or MO. MO is molecular orbital. So MO are associated with the entire molecule, not a single atom. So when you have atomic orbital, we talk about the space around the nuclei of this atom, where you can find, where you can have high probability to find electron. That's the atomic orbital. Now you extend this concept to the molecule. That means we have concept of molecular orbital. It's the space in the molecule surround where you can find, where you can have high probability to find electron. That means the electron density will have high probability to localize in this space. Okay? So you consider the molecule, not only atom. So we combine, we start by the combination of the atomic orbital by the concept of, we call linear combination of atomic orbital. Okay, linear combination of atomic orbital. So that means when you have two atoms, hydrogen, approach to make a molecule H2 in the valence bond theory, to say that the two orbitals overlap to create the sigma bond. The two orbitals need to approach, get closer, and try to optimize the distance, to optimize the attractive and repulsive interaction. Now, in the molecular orbital theory, the chemist states that the two atomic orbitals will combine by the linear combination of atomic orbital, combined by a linear way. That means one orbital s and one orbital s will generate two orbitals. 1 + 1 = 2. Two orbitals. And among the two orbitals, you will have a one which called the bonding orbital, which has lower energy than the atomic orbital. And you have a second orbital which have higher energy than the atomic orbital. We call anti-bonding molecular orbital. So one atomic orbital plus one atomic orbital provide two molecular orbital. In two molecular orbital, you have a 1/2. That means one molecular orbital, which is a lower potential energy. We call bonding molecular orbital. You have a second orbital, which has higher energy. We call non-bonding molecular anti-bonding molecular orbital. Okay, that's the first thing. Then we pick up electron of the two atoms, because now they combine together. So one electron from one s, another one electron from the second hydrogen. So you have in total two electrons. So the two electrons will occupy the lower energy bonding orbital with a lower energy than the isolated 1s atomic orbital. So you can imagine now, when the two orbitals combine and generate two molecular orbitals, one at the lower energy level. So the electron now, if they occupy the bonding orbital, will have a lower energy. And if they occupy the anti-bonding orbital, they will have a higher energy. So in the molecule of hydrogen, is because X hydrogen bring one electron s. So the two hydrogen will have a two electron s. So if the two electron s occupy the bonding orbital here, the total energy of the system will be lower. And I had mentioned to you, that is the driving force to making the bonding. Because when hydrogen and hydrogen bond, both the two atoms lost their freedom, lost their entropy. So they need to gain in terms of energy, in terms of enthalpy. So here the case, when they put the two electrons in the lower energy orbital, so the total energy of the system will be lower. That means the molecule is more stable. So they gain the stability, so they can sacrifice the freedom to get higher stability. Okay. So remember, energy is the driving force of the chemical bond. If the moment you cannot gain in terms of energy, then it's better you separate. The bonding will be not formed. The two atoms become independent. Okay. So let's look at the case of the helium. Because helium has electron configuration of 1 and 2. So the one helium atom have two electron valence. So if you put two atom helium, in total you have 4 electrons. Let's consider the combination of 1s helium and 1s helium. orbital. You will have two molecular orbital, one bonding and one anti-bonding. And bonding at a lower energy, anti-bonding at higher energy. Now, the two helium have total 2 plus 2 equal to 4 electrons. And you remember that each orbital can accumulate, can take only 2 electrons. So you put 2 electrons in the bonding and 2 electrons in the anti-bonding. So now the total energy of the system equal to 2 times energy of the MO bonding plus 2 times MO anti-bonding. So 2 times of energy bonding, it has lower energy than the average, and 2 times of anti-bonding have a higher energy than the average. So basically this will exactly equal to energy when the 2 helium free. So it means the 2 helium atom would not form any chemical bond, because when they, in the case they form chemical bond, through the molecular orbital theory, we understand that they cannot gain anything in terms of energy, but they lost the freedom, they lost the enthalpy. So the process cannot happen. Okay, naturally, they don't prefer that. So now we come to take consider both the electron in the molecular bonding orbital and anti-bonding orbital. We have a concept of the bond order. The bond order reflects the stability of the covalent bond. Higher bond order, that means the bond is more stable, and also shorter bond. So the bond order equal to number of electrons in the molecular bonding, in the bonding molecular orbital, minus the number of electrons in the anti-bonding molecular orbital, you divide by 2. Because why you divide by 2? Because one bond, one covalent bond, take 2 electrons. So you calculate the number of electrons between the bonding orbital and anti-bonding orbital, you divide by 2, you have the number of bonds, that means the bond order. So take the case of hydrogen, you have number of electrons in the bonding orbital is 2, number of electrons in the anti-bonding orbital is 0, that means 2 minus 1 equal 2 minus 0 equal to 2. So you divide by 2 equal to 1. So that means the bonding between the hydrogen and hydrogen have a bond order of 1, and here you have a single bond. For the case of helium, you take 2 electrons in the bonding minus 2 electrons in the anti-bonding, you divide by 2 is equal to 0. That means bond order equal to 0. That means there's no bonding, so the bond will not be produced. So now imagine that if you have one molecule with A2 minus 1 electron, so you have A2 plus. So that means here you have only 1 electron. In that case, the bond order will be equal to 1 minus 0 divided by 2, it will be 0.5. So the famous 0.5 bond order that we discussed previously when we talk about the bond order, and I asked you guys, is it possible to have a bond order not integer number but different? You can also imagine that the molecule H2 plus 1 electron to make H2 minus. So in this case, because the 2 electron already here in this bonding orbital, so we will have 1 electron added to the anti-bonding orbital. So now the bond order will be 2 minus 1 divided by 2 is equal to 0.5. So you see that you can make the bond order hydrogen both by reducing hydrogen, that means adding 1 electron, or by oxidizing hydrogen by remove 1 electron. And I mentioned that the bond order smaller, that means the bond become longer. So that means when you move from the molecule hydrogen with the bond order 1 to A2 plus, bond order 0.5, that means the bond, the distance between hydrogen and hydrogen in the A2 plus become longer than the distance hydrogen in the A2. So that means you can easier to break the hydrogen bond in the H2 plus or H2 minus compared with H2 neutral. Okay. Sorry. Okay, so take a look in the other molecule like lithium. You have a single bond. For the case of barium, you have a no bond, order equal to 0. Quite easy to understand. This I explained already. So this we can keep. So we can see that again explain that helium is not stable. It's not more stable than helium atom individual. So there's no tendency to make the chemical bond, because if you cannot gain if you cannot gain anything in energy, the bond will be not produced. So thus we talk about the sigma bond, the sigma bond between the two molecular orbital. So now we move to the other 2p atomic orbital, how the 2p atomic orbital can mix together to make the molecular bond. Before we talk about 2s atomic orbital. So for the same 2p orbital, you have BZ, so they can mix. So you have two molecular orbital, one bonding and one anti-bonding. So depending on the direction of the p orbital, you can have different direction of the orbital p. So here you have a sigma. So you have a sigma MO, and here you have a p MO, right? Because it's overlapped by side, and here it's overlapped by heat. Okay. So here is a complete diagram of the molecule where you take both the orbital 2s and orbital 2b to make the combination. So you see there's one orbital s and one orbital s of two atoms, A and B, if you want. Let's say molecule A. Let's consider the molecule A. So one S of A and one S of A. So you have a two molecular S, and you have one S bonding, one molecular S anti-bonding. You have three orbital B. So by the linear combination, in total, you will have a 6 orbital, molecular orbital. Among 6 molecular orbital, you have a 3 bonding molecular orbital and 3 anti-bonding molecular orbital. Anti-bonding molecular orbital will have higher energy than the bonding orbital, molecular orbital. So you can see that in terms of energy, they will be symmetric in terms of position compared with the individual atom. Okay, so okay, important thing. This diagram is applicable for all the atoms which have main number over than 8. So it starts, this diagram can be applicable for oxygen onward, from the oxygen atom onward. So for the atom with the main number smaller than 8, like nitrogen, then we need to use a second diagram standard. The second diagram come like this one. It's due to the sigma S and sigma B interaction. So when you have a S and B interact, you have a splitting. So that is for the K of, this is for the K of Z higher than 8. So for this smaller than 7, then you have interaction between the S and B. Because of this interaction, so you have the splitting. So the B will become higher energy and the S become lower energy. While for the anti-bonding, there are no interaction, so they keep the same energy level. At the end, what will happen? You will have the inverse. I will show you here. So you see here, because of the interaction, that's the orbital sigma p will have a higher energy than the pp. Okay, for the case of z smaller than z higher than s, it will be inverse. But because of interaction, though, it be switch. So basically, this slide summarizes two molecular orbital diagram that is normally used at the general chemistry class 1 class to work on the electron configuration of the molecule. So for the case of Z over H, that means start from oxygen onwards, you have this standard one. And for the Z smaller than 7, from the nitrogen backward, you have the second one. Basically, during the exam, I see you to provide the two diagram. What I need, I would like to ask for understanding is which one you apply, and in the case you apply the two diagram, what could be the consequences on the physical chemical properties that we discuss later. Okay, we do not need to remember the two diagram. So now we have another property which already we discussed in previous class, but here we talk about the magnetism. So we have a diamagnetic substance is a substance whose all of electron are pair. That means the total spin equal to 0. So when it is diamagnetic substance with the total spin equal to 0, it is weakly repelled by a magnetic field. In other words, in the other case, you have a paramagnetic substance. That means a substance with one or more unpaired electron. That means the total spin of this compound different than 0. And because it have unpaired electron with a spin different than 0, so it attracted by the magnetic field. So the order, the degree of this magnetism, we can do the measurement experimentally. It's quite simple. Let's say you put the sample in a balance. So if you have, and then you put a magnet, if the compound has the paramagnetic property, it will have a repulsion with the magnet. So you can see, by the balance, you can measure the difference in mass. So from the difference in mass, you do the measurement, you can quantify, you can deduce back the order of the magnetic. So now we go one by one, diatomic molecule. Let's say for the lithium, the bond order is equal to 1 and all electron are pair. So you have a diamagnetic compound. For barium, bond order 0. So there are no molecule, we do not discuss anymore. For borons, you have, you see here, thus you have 2 electron unpaired. So in total, you have a bond order 1. And in this case, you have total spin equal to 1 as well, because each single electron have half spin. And in this case, you have a paramagnetic. For the carbon, C2, then you have all electron pair. The bond order is equal to 2. But the compound become diamagnetic because the total spin equal to 0. For the nitrogen, the bond order it become 3. Because you have in total 6 electron in the bonding molecular orbital and 0 electron in the anti-bonding orbital. All electrons are pair, so you have diamagnetic spaces. So you see that oxygen, the nitrogen is diamagnetic, right? Remember, oxygen is diamagnetic with the total spin equal to 0. Next, when we look at the oxygen, then you have 6 electrons in the bonding orbital and 2 electrons in the anti-bonding orbital. So in total, you have 6 minus 2 equal to 4 divided by 2. So the bond order equal to 2. So that's why you know that oxygen have a double bond. And then it's paramagnetic because it have 2 single electrons. And in that case, the total spin S equal to half plus half equal to 1. So you see that's the difference between the nitrogen and oxygen is that the oxygen have a 2 single bond and oxygen have a 0 single bond. Okay. So for the heteronuclear diatomic molecule, like for the case of NO, you know that the oxygen and nitrogen have a different electronegativity. So you use the same diagram like O2, but then you have lower energy for the case of oxygen because it's have a higher electronegativity. Then not very special thing. The thing is that you keep the same the molecular orbital diagram like O2, but you put in the 2 different level of energy, nitrogen and oxygen, given that oxygen have a lower energy level because it's attract electron, so it's get lower energy. That means also in the molecule and in the case of the molecule NO, you see that the nitrogen have a 5 electron and oxygen have a 6 electrons. So in total, you have 11 electrons. So what you can see here is that the molecule NO have 1 single electron in the antibonding molecular orbital and 6 electron in the bonding molecular orbital. So in total, you have 6 minus 1 divided by 2. The bond order is 2.5. And you have 1 single electron here. So that explains why the molecule NO, with a single electron have a tendency to make a dimer NO like this, NO2, because it have a single electron. So imagine that if you have 2 molecule NO, this single electron, 2 single electron become a pair. So it's will have the tendency to make a dimer. So now we come to the end of our lecture already, but before we end, I would like to invite you think for one question. We understand as oxygen and nitrogen both exist in our atmosphere. Is it correct? So in our air, in the air surround us, we have about 78% of nitrogen and 20% of oxygen. They exist, they are both stable. That means there's no reaction between the nitrogen and oxygen. That means there's no reaction between the nitrogen, oxygen, of the atmosphere. Okay? But when you have a nitrogen and oxygen, and then you have storm, when you have lighting, then you can make a reaction happen and become NO, NO2, and so on. So in Vietnamese expression, we say that there's a one expression. I don't know how to translate in English. But I'm sorry. So if you don't understand Vietnamese, but they say that lúa chiêm nấp nó đầu bờ, hễ nghe tiếng sấm phất cờ mà lên. You understand that, right? So it say that when you plant rice, and then when you have lighting in the atmosphere, then rice can develop, the plant can develop very well. And thanks to this reaction, we call the nitrogen fixation reaction, if you want, because this nitrogen in air, the plant, the rice cannot up, but when you convert into NO, NO2, and so on, it can become nitrate, and then some microbia can take it to make Na3 and then from that you can get into urea, so on. But my question is, why at the ambient condition oxygen and nitrogen cannot react, but when they're lighting, then the reaction happen? The second example I invite you guys to think is, let's say, if you take molecule CH4 and oxygen, you open the two cylinder of CH4 and oxygen in the same room at the room temperature without any excitation, then they will not react. You can smell the gas, but it's not flame. But then if you lighting, if you do the lighting, you do the excitation, you light on, then the reaction happen. You make CO2 water and a hue of energy. That means the actual reaction is exothermic and spontaneous, but without the lighting, the reaction will not happen. Oxygen and CH4 can coexist stable in ambient condition. So what make happen? What make the reaction? What make the two compounds stable as the ambient condition, but then violently react at the excitation condition? Anyone can comment? Do you understand the problem I explained?
Yes.
Yes.
Okay. So anyone can comment on this based on the concept of molecular orbital.
Well, I think that maybe in the room temperature, they do not react together because they have the difference in the energy level. But when there is lightning, then one is excited, and maybe the difference in energy is lower. So and their energy level is come closer together, so they can react. I think so.
Okay, thank you. Any other idea?
Maybe this reaction require an extremely high activation energy, and therefore room temperature wouldn't be suffice.
Mm-hmm. Okay. Why the reaction need a huge activation energy? What could be the reason for this?
So I think the reason would be O2. In the structure of the O2, there are double bonds, and in the structure of N2, there are triple bonds, which are extremely strong.
But then in the case of CH4, you have own single bond. Huh?
So that's true.
So okay, because the time is run out, the very important thing is that in the chemistry, the observation is like react with like. So similar for the Gen Z's like you guys, like mấy tầng nào gặp mấy tầng đấy, okay? So okay, let's say for the nitrogen, you see that nitrogen here, you have all the electron pair, right? So basically S equal to 0 here. So we take the S big equal to 2S plus 1. So equal to 2S, that means 0 plus 1 equal to 1. So that means we call the singless. By the definition, when you have a total S equal to 2S plus 1 equal to 1, that means singless. And if you have a species which S equal to 1, that means 2S plus 1 equal to 3, we call the triplet. Okay, that's the first thing. So by understanding the similarity, that means like react with like, singlet react with singlets, triplets will react with triplets. So for the nitrogen, you have singlets, all the electrons are there. When you move to oxygen, you see that the oxygen have 2 single electrons, right? So in total, S equal to 1 because 2 times half. So it's become triplet. So the oxygen in the air is a triplet oxygen. While the nitrogen is singlet, so the nitrogen oxygen cannot react because singlet react with singlet, triplet react with triplet. How about CH4? In the CH4, all bonds are already a pair of electrons. That means the total spin of all of this single bond is 0. That means the bond here is also singlet. So that's why oxygen cannot react with CH4 at the ambient condition. Now, when you lighting up, like as you mentioned, you do the activation. So you provide energy to move the electron from the single electron from here to this one. So you make a pair of electrons to convert triplets oxygen to become singlet oxygen. And by doing so, you make the singlet oxygen react with CH4 and also react with the nitrogen. And because the reaction is exothermic, that means it really heats. So more reaction happen, more heat is released, more heat is released, you have more energy to combine single electron to become a pair of electrons. That means you convert more triplet electron to singlet electron. So to stop the reaction, you have no other choice to remove oxygen. You need to remove oxygen because when you remove oxygen, then no more oxygen become singlet. So the reaction will stop. Because when the reaction stops, it's already exothermic and it generates a lot of heat. All the oxygen surround will be excited. And then the reaction progress. You get what I mean?
Yes.
Okay. So that's the purpose. It seemed quite interesting. Now, another question for oxygen. Then we discussed last question and then we start. Give me, let's say 5 more minutes because it's very interesting in my eye. Let's say, look at the K of oxygen here, right? Take the K of oxygen here. Okay. Then, when you learn chemistry at high school, your professor say that oxygen plus 2 proton plus 2 electron, it can make a product. The second possibility, oxygen can be reduced by 4 proton and 4 electron to provide another product, A and B. Okay? So what could be A and B? And why A and B are produced in this case? This reaction seemed to me at high school seemed to be very simple one. Almost everyone can remember. But now in industry, it's extremely important. It decides how we can move onward toward the sustainable economy, sustainable energy. For example, when you run the when you replace, let's say, all the car running with fuel cell, running with the fossil fuel like petroleum, by something run with hydrogen gas, right? Then you need the reaction hydrogen plus oxygen provide water. Huh? To make this reaction happen, then hydrogen need to be oxidized to become 2 electrons, and then oxygen need to be produced or reduced by this reaction. So basically 2 compounds like this. So the 2 reaction will decide how the car can run with hydrogen fuel. So you see how important a simple reaction is to the industry. So now, if you just look at the molecular diagram, can you predict the product A and product B? What could be A and B? That will be my last question of today's lecture. Please. Anyone?
I think
Anyone
A,
can
OH,
A is
OH minus.
OH minus, okay. A equal to OH minus, and then B,
I'm still thinking about B.
okay. But why OH minus? How you can come out with this prediction?
Okay, so I think that the two electron minus here will come into the orbital, to orbital in O2.
Mm-hmm.
So it will.
Okay. Okay, I see one of you already provide a correct answer. So A should be A2O2 and B water. Why? So in the case of A, right, you have 2 electrons. So you put 2 electrons here in this molecule. So with 2 electrons, now the bond order will be 6 minus 4 divided by 2 equal to 1. That means the product should have oxygen single bond. So you put 2 proton inside, so it will make A2O2. Now for the case of 4 electrons, that means you need to add up more 2 electrons here. So the bond order will be 6 minus 6 divided by 2 equal to 0. That means there's no bonding between oxygen and oxygen. So you put product like this with no bonding. So it's water. Is it clear?
Can you explain how can you count the bonding and anti-bonding pairs of electrons?
Okay. Okay. So the oxygen is like this, right? Okay.
Yes.
So now I look at the reaction of O2 plus 2 electron plus 2 proton, right? So I need to add 2 electron in the molecule of 2, right? So because when I put electron in the molecular orbital, I need to put from the lower energy to the higher. So I put 1 electron here and 1 electron here, right? So 2 electron equal to 2 electron I add here. So now the bond order of product A will equal to, so you have total bonding electron. So here you have 2. So in total, you can calculate like 2 plus 2, 2 and 2. So plus 6 minus 2 here minus 4 here. Okay. So divide by 2. So you see that the bond order will be 1. Okay. Bond order will be 1. That means in the A, I should have oxygen single bond. So because I add 2 electrons, so it becomes 1 negative here, 1 negative here. So I put 1 positive of hydrogen and 1 positive of hydrogen. So I will add A2O2. Is it okay?
Yes. Thank you.
Now for the case of O2, plus 4 electron plus 4 proton, I will put 4 electron here. So already 2, so it remains 2 electron here. So in total now, I make the calculation. I will have a bond order equal to 0. Bond order equal to 0, that means I start from oxygen bond like this. The product will have no bond between oxygen and oxygen. So I should remove this, okay? And because I have 4 proton, so I put 4 proton here. So I have 2 molecules of water, okay?
Yes.
Yes.
Okay.
Now, the last question for you guys to think about this at home. If I take the same oxygen, okay, I have a one enzyme. I have oxygen. I have a one possibility to reduce by 2 electrons to make A2O2. So here I have A2O2. And I have a second possibility to have A2O. Which one is easier? A2O2 production or A2O production? Which one is easier? This is important because if the production of A2O2 is easier, that means when we run the gas, we will produce A2O2. But if it's easier to make A2O water, then mean when we run the car with hydrogen, we will produce only water. A2O2 is quite toxic. A2O is not toxic to the environment. So it depends on the which one is easier, then my technology can be adapted in the future. So based on the understanding you have today, in your opinion, which one is more difficult? Which one is more easier? Production of A2O2 or production of water? Do you understand my question? Section will be the last class of general chemistry. So thank you for your attention, and then see you next week. Bye bye.
Bye, Professor.